Hello everyone, my name is Prajakta Kulkarni. I have been doing this course Managing Machine Learning Projects from Duke University on Coursera. This video is to explain my solution for the course project. So the opportunity that I have considered is automation of annotation tool. This can reduce a lot of manual efforts and generate more and more labeled data for the MLDL models in less time. For any MLDL model to work accurately, huge amounts of training data is required. Generating this data involves capturing as well as labeling the data. Labeling is usually a manual process which requires a lot of efforts and time. So the idea here is to utilize the ML model itself for simplifying this tedious process. ML for ML. Let's do the opportunity evaluation for this solution. Is there a problem? Yes. MLDL models need a huge amount of data to learn and perform well. Generation of labels manually is a huge effort and takes significant time, even more than model development itself. Can ML help solve it? Yes. A small model or even the model that is to be used in turn to predict the objects can be trained on a smaller manually annotated data set to generate labels for the next images. This way, the manual job can be reduced to verifying and correcting the labels whenever necessary. Does someone care? Yes. This process will save a lot of manual efforts and time. The manual annotators can be relieved as their work will be automatically done at least halfway through. This can reduce the number of annotators required, number of machines required in turn to generate labels for the entire dataset. Now, let's define the problem as per the CRISP-DM business understanding. The target users here are the manual annotators who have to sit and annotate each and every image. The problem statement can be defined as generate automatic labels so that manual effort is reduced to only verifying and correcting the boxes instead of drawing them from scratch. Today, too many manual annotators have to spend a lot of time with the annotation tool to label the images, drawing bounding boxes around the objects and labeling them. This is very much tiring both mentally and physically. This solution can reduce the stress on manual annotators. In order to define success, we look at the outcome matrix and the output matrix. The outcome matrix here would be saved time and cost, mainly of the annotators, as at least half the work would be done by the model. This can also let the ML team focus on the ML development more, as data will be available quickly and model development will keep happening every step of the way. No need to wait for complete training set. Also, while the next set of images are getting annotated, there would be enough time to perform some experimentations to know the model, know what works, what doesn't, and improve the model. As far as the output metrics are concerned, I would want to stick to IOU, that is intersection of union. This will ensure the predicted bounding box covers most of the part of the object under consideration. Moving on to the factors, we will have to identify the classes for the model based on requirement. Depending on the classes and input images, model to be used needs to be identified. Also, the precision of annotation needed has to be taken in consideration. Let us look at the validation plan now. Firstly, a few images should be selected from the captures, making sure that we cover as many different scenarios as possible. These selected images should be annotated manually. Using this set of labeled images, a basic model should be trained. This can be actual model that needs these input images or a simple smaller network. After looking at the predictions on new images, the model should be fine-tuned with hyperparameter tuning. Even though the model performance can be expected not to be at its best because of smaller dataset, the prediction should at least not be annoying to the manual annotators. Meanwhile, the task of manual annotation should be ongoing, and newly annotated images can also be added to retrain and improve the performance. The annotation tool must now be loaded with the new image, choosing the model to display the best predictions on top of it. The manual annotators will then have to add missing boxes and correct the predictions if needed. For validation, it is extremely important keeping an eye on model's output and amount of correction work needed on top of it. It is equally important to keep adding newly annotated images, which can either be generated manually or by doing corrections on predictions to the training set and retraining the model. After every retrain, fine tuning is necessary too. As far as ML system design is concerned, there are following considerations. Cloud versus edge. The model can be deployed on cloud to have a certain number of predictions at once, which can then be loaded in the annotation tool, or the model can run on the fly with the tool to generate predictions on every newly loaded image. Online versus offline, the predictions can be online or offline depending on how the model gets integrated with the tool, predicting for every image on the go or an entire batch. The retraining should be offline for sure. There is no point in retraining the model until there is a good amount of newly labeled images. Batch versus online predictions. Any of these should work as discussed earlier. Looking at the potential risks in production for this project, there are chances of data as well as concept drift. As far as the data drift is considered, the changes in scenarios like background, corner cases, number of objects per image, and object density all can lead to dropped accuracy for the model, making the predictions partially or fully useless for automation. This would require another round of manual annotations to create more training data and retraining on top of it for these new scenarios. For concept drift, there could be addition or deletion of a class altogether depending on the objects to be considered for actual model usage. This might need rework for generating original labels and altering the model for new classes and retraining. Another concept drift could be using the model for a new use case with different types of images, different classes, and different precision requirements. But this can be looked at as a new problem statement for the same solution and can be worked on following the same steps since the beginning. That's it. Thank you.